Hello fellow skeptics, I'm Luther Name, and this is the 13th video in a series on the broad topic of is something wrong with modern physics? If so, what? And can it be fixed? Now in the last few videos I've been talking about the Doppler effect and the aberration, propagation of electromagnetic radiation. And I've given some examples of how we use that. It has both academic and practical or technological consequences. And what I've been doing is exploring a few of those. In the intro to the last video, I said I was going to be doing a little bit more in that video than I actually did. What I thought that I might include in that video, I'll include in this one. The last one I focused on the integration of the Doppler effect and the aberration effect as identified by Einstein in how they impact radiation pressure. And radiation pressure is an important consequence of how we detect radiation, the presence of radiation. Whenever radiation interacts with matter, we see an effect of one form or another. It could be spectral, could be a pressure, a force, and that's how we know that there's radiation present. Otherwise, we have very few ways of knowing that there's in fact any radiation present. And I also talked about how many of the things that we can accomplish by considering the Doppler and aberration effects have been interpreted as being kinematic effects, and they're not. They're kinematic only in the sense that what we're doing is seeing how physical objects are affected by their interaction with electromagnetic radiation. Those particular effects we've called the kinematic effects, and they've been identified erroneously as relativistic effects, and the magnitudes are wrong, and what we've shown in the last few of the videos that many of the elements that we consider to be important to special relativity, in fact, don't exist. They're figments of everybody's imagination. What we're doing is misinterpreting what are legitimate electromagnetic effects and their consequences in terms of kinematics as being relevant to the kinematical part of relativity, which doesn't exist. Minkowski's reformulation doesn't exist. It's a fake. In fact, I think one of the more spectacular negations that came out of the analysis is that there's no such thing as the addition of velocities. You just add velocities like you normally would. There's no limitation on the speed of anything other than our inabilities to get things up to those speeds. And there are many impediments to being able to reach the speed of light. And we've discussed a few of those. So in this one, though, I'm going to be talking almost exclusively in terms of what the aberration effect brings to the ball game. It has both academic and it has technological consequences. And one of the things I alluded to was I think there's an unknown technological aspect of the aberration effect, and I've been spending a little time trying to understand why we haven't seen the consequences of the aberration effect itself. And this goes back to one of the things that I've talked about before, and what I'll elaborate upon in this video, is that we don't fully understand completely how all our measurement processes work. We don't understand everything that's going on in our telescopes, in our various pieces of electronic equipment. We just don't have a handle on all the physics that comes into play. And I'm going to talk about some of those. And most will have mostly an academic impact. There are issues that have been around for a century that physicists, academic physicists, have pondered, haven't been able to come up with a conclusion. They've invoked all sorts of peripheral physics, but I think that the aberration effect actually provides a means of addressing some of these. It may not be the whole means, but it certainly is another tool and it gets you a lot closer to an explanation of what's going on. So that's what I'm going to be talking about in this video, is the aberration effect and what's going on. And like I alluded to before, in terms of the Doppler effect radiation pressures, it turns out that we're missing half of the consequences of the interaction of radiation with materials. And the radiation pressure, we're missing half of the effect. We attribute most of the kinematics that occur to the Doppler effect. But in fact, the aberration is another 50% of what the interaction is, if you look at it the correct way. So that's what we're going to talk about. And we're going to get to the visuals then that I put together to support these contentions. So in order to show what the impact of the aberration is on the Doppler, what we're going to do is use two scenarios. The scenarios are important because they highlight things that can be measured or can be physically measured. And so even though we have a Doppler expression, we have to understand how we measure that Doppler and how that Doppler can impact any dynamics or anything within the system that we're looking at within the scenario that we can measure. And that's the only way we can know what's going on, is by measuring it. So that's what we're going to do here. In the first scenario, what we're looking at is a solar sail in Earth orbit. And as it starts out, it's under the influence of direct solar radiation moving radially out from the sun past the Earth's orbit. And the Earth is moving perpendicular to that flux at a speed of 30 kilometers. And what we have then is a transverse beta, which is V over C, that reduces to 10 to the minus 4. Usually if you get down to something that's 10 to the minus 2, sometimes even less, even larger number than that. In estimating or approximating various complicated functions like we have up here, we can use a small beta approximation where we can then estimate the size of these in terms of keeping terms in a series expansion. It's just a well-known aspect of what we're doing. So what we do first here is, this is the scenario. You have a solar sail, you have radial flux coming from the sun, you have the solar sail initially moving in a direction VT, transverse velocity relative to the solar flux, and you have then the solar flux providing a pressure, and the pressure provides a force that accelerates the sail radially outward along the direction of the flux. And so the ultimate velocity of the object itself is just the vector sum of these two forces. So what we have though is this. So when we take a look at this thing, this expression for the radiation pressure, again noting that the static model is the only model that's currently accepted or used. These are not only are not all of the elements of this function recognized, anything having to do with the Doppler is basically dismissed as being irrelevant. But let's see what the relevance really is. When we take a look at what this term is, and we look at it in what I call the small beta approximation, what we can show is that this all can be reduced down to this one, this simple function right here. Therefore, the actual radiation pressure that's being experienced by the object is given by the static pressure multiplied by this, which means that the static pressure is being modified by this small component given by the radial speed that the object has. When it first starts out, this is very small. Therefore, and close to the Earth, when the object is first beginning to move, the radial velocity is so small that it's very difficult to detect this radial component. It takes time for this to build up. And it's negative. What it does is it decreases the effective magnitude of the radiation pressure. Therefore, if you were looking and actually measuring what's happening to a sail over a period of time, it would not seem to have gone radially as far as you expect because you're using this model, whereas this is the model.
it's not being affected by the same magnitude as you normally would expect. You can measure that. The thing to note is that the aberration effect is strictly a dynamic effect. It does not occur if we're only looking at the static radiation pressure model. The aberration effect only occurs through this particular dynamic term or component of the radiation pressure. And as you can see, this is where the angle phi comes into play. And what we do is we modify it again so that we're looking at the proper geometry, not the geometry that was used to derive the Doppler and aberration equations, but in fact, the way we would make measurements and the way the actual physics works in terms of what's happening. As the object moves laterally across the flux, what happens is that there's an incremental momentum shift that occurs in the photons as they're reflected from or even transmitted into the transversely moving object or the object that has a transverse velocity. What we see then is when we add a component to the reflected radiation in the transverse direction, we have a recoil effect on the object itself. So that the effect is that we have the aberration effect, which moves the photon or directs the photon in the, with an added component of momentum, which changes its energy level also. And what we experience in the way of a force would be the recoil force associated with that deflected photon. So when we take a look at all those terms, looking again at how we make the small beta approximation, we find out this is we have the direct component, but we have this is the modification. This is the actual change in the transverse component of the pressure. And since phi is equal to 90 degrees, sine phi is equal to 1, and we're left with then a transverse pressure, effective pressure, given by that small recoil, given by this term. And when we substitute in for the static model and the dynamic portion of it, and multiply that times b sub t, we're left with a term like this. However, br times bt is so small it can be ignored, and so we have then that the transverse component of the force is given by just the static component times that small transverse beta that we had. So what we wind up with is that the dynamics of the object are impacted in two ways. One is the direct Doppler is decreased by a small amount given by the radial Doppler that's been picked up, and it has now a new unknown transverse component given by the transverse motion times the static model. Since they don't model this, then they see that the object is moving, when they make a measurement, it's moving not only slower outward radially, it's got an unknown source of transverse momentum that's kind of moving it in a retrograde or allowing it to move in a retrograde motion that is unanticipated. And so it's unknown. They don't know what's going on. So what we have and this is just to summarize what I just said, we have two forces that are acting opposite the motion of the object. This is the static portion of it, and what we have is the Doppler decreases the effective magnitude of the radial component, and it adds a new transverse component that moves in the opposite direction of the orbital motion of the object itself. So that's one scenario, and those are some measurable amounts, measurable quantities that would tell you that something is happening. At this particular point, they know that things are happening, but they use all sorts of hand waving and arguments and to try and explain it because they don't know what the complete physics is that they're working.
As I began to work through the various scenarios, I realized that was probably the best way to describe the details of what was really happening with the Doppler and with the essentially unexploited and unrecognized features of the aberration itself. And so as I began to develop the scenarios, I realized that each one was maybe getting a little bit too long for a single video. So I decided to break this video at this point, where I'm going to continue with some other aspects of the aberration in the next video that deal with another feature, which has to do with the actual frequency, change in frequency associated with the presence of the aberration itself. In this video we talked about the Doppler and the frequency shift, and the next video, the video after the next video, I'm going to do another major scenario with a feature that will be a bit surprising. By putting them all together, the result will be something totally unexpected. A feature of the combination of the Doppler and aberration that will feed the narrative that I've been making, that we really don't know what we're measuring. We don't know really how our measurement apparatus work. We've just missed so much physics. We're very good technologists. We can build things to measure things, but we don't always know what we're measuring, or even how to interpret what it is that we're seeing. So I'm going to get into that. And just recall, I'm not inventing new physics. What I'm doing is exposing existing physics. It happened back when I began this series talking about the Newtonian physics and the things that we've missed associated with it, and how those things that we've missed have flowed forward in time 300 years to the present, and have caused issues in terms of whether we needed new physics to explain things that were not being properly explained because we simply didn't get Newtonian physics correctly. So again, I'm Luther Name. Stay skeptical. Leave a message or an element for discussion, and I'll see you in the next video.